Well, with reference to our discussion on the real numbers, in this tutorial, we are going to talk a little bit more about the rational versus irrational numbers, okay? So our learning objective is threefold. One is that we want to give a quick revisit on what have we learned in our previous grades about the rationals versus irrationals, all right? And the second is assuming we know that there is a rational number in the form of P over Q. If that rational is converted into its decimal equivalent, will that result into a terminating decimal number or a non-terminating but a recurring decimal number, right? And the third is we want to discuss a little bit more about the rules on operations on the irrational numbers, all right? So let's go take a look at these three objectives. And to begin with, we know that the real numbers, they can be divided into two main categories. One of them is the rational number, right? And the second is irrational. That's what we are going to talk about today, of course, right? And we know that any rational is written in the form of P over Q, where P and Q are integers such that Q is not equal to 0. If any number can be converted into this form, then we say that that's a rational, otherwise it is an irrational number, right? If it is not in the form of P over Q, then it will be an irrational number. In addition to that, we also looked at these criteria that if any decimal number, if we take it, if the decimal part terminates after a certain while, then it is a rational number. If it is not terminating, but the decimal digits, they repeat themselves, then it is called a recurring decimal digit part, right? And those two kind of categories belong to the rational numbers, right? Otherwise, we say that any other number, either not in this form or not in this form, will be called as an irrational number. So these are some quick rules we need to keep in mind whenever we talk about rationals versus irrationals, right? But in addition to that, we want to spend a little bit more time talking about that if you are already given a number in this form, how do you quickly identify whether that number will result into an equivalent decimal and whether that would be a terminating decimal number or a non-terminating but a recurring decimal number, okay? So that is our second part of this tutorial. Let's go take a look at that. So we begin by defining this definition that, let's say, there is a number, let's say that number is in the form of P over Q. It's a rational number such that the prime factorization of Q, the denominator, is in the form of 2 to the power n, 5 to the power m, right? Where m and n are non-negative integers. Therefore, whenever you can convert the denominator of any rational into this form, then you will say that that rational number will result into a decimal equivalent having a decimal expansion that terminates, right? If Q cannot be written in the form of 2 to the power n, 5 to the power m, then it will result into a rational number, the one that will have a non-terminating decimal expansion. Okay, so let's take a look at an example. And the task is, without carrying out the actual division, find out if the following rational numbers have a terminating or a non-terminating decimal expansion. First example, 35 over 50, right? Let's break them down into their prime factors. So let's say 35 is 7 times 5, and then you have 50, that will be 2 times 25, or you will say 7 times 5 divided by 2 times 5 square, right? And you can say with ease that this denominator here, it can be equated to 2 to power n, 5 to power m, right? So n and m are non-negative integers, correct? Hence, we will say that this is a decimal number that has a terminating decimal expansion. And when you actually carry out the division, you will find that 35 over 50 is 0.7. So this proves what we have found. And the second is 15 over 160. So when you expand those numbers, you will say that this is 3 times 5 and the denominator is 2 to the power 5 times 5. You must carry out this multiplication to check my mathematics. But you see, the point is that this denominator here, it can be equated in the form of 2 to power n, 5 to power m. So we say that this number will also result into a decimal number which will be terminating in nature, okay? And our last example is 5 over 21. So when you take this number, 5 over 21 is 5 over 3 times 7, which is not in this form, right? This denominator here. So number 5 over 21, when you actually divide it, you will find that it is non-terminating, right? And that is exactly what we have found here. So this theorem, it actually gives you a quick trick that if there is any rational number p over q, how do you know that whether that number will result into a terminating versus non-terminating decimal digit? Now let's talk about some of the rules on the irrational numbers. So there are three key principles that you always need to keep in mind whenever you are operating on irrational numbers. First one is, if there is a prime number and if you take a square root of that prime number, then it will always result into an irrational number. So a quick example could be that, let's say 2 is a rational number and it is a prime number as well. So the moment you take a square root of 2, it becomes irrational. Likewise, 3 is a prime number, but when you take square root of 3, it becomes irrational. Next, the sum or product of any rational with irrational number will always result into an irrational number, right? So my first example is, identify that if this number 3 minus 2 times square root of 7, would that be a rational or an irrational number? So I will say that this is an irrational number. Without actually doing any operation them, we can tell them that it is an irrational number. So how do we come to this conclusion very quickly? I know that 7 is a prime, right? So if 7 is a prime, then square root of 7 will be an irrational number. Now you multiply this irrational with a rational number 2, then it will also result into an irrational number. Now you reverse the sign on this and then you add this number into another rational number, which is 3, but this number is this, so this will also result into an irrational number. So this is how we quickly identify that whether this is an irrational or not. But let's say that I want to prove that this is indeed an irrational number. So what we do is, let's say that 3 minus 2 times square root of 7. Let's say this is not irrational, this is a rational number, right? And I say that this is equal to x, where x is a rational number. So now let's do some transposing here. So I will do is 3 minus x becomes equal to 2 times square root of 7, or when you divide both sides with 2, you get 3 minus x divided by 2 is equal to square root of 7. But what is this term 3 minus x divided by 2? It will be a rational number. So this is in the form of p over q. Hence it will be a rational number. But we know that square root of 7 is an irrational number because 7 is a prime number and we took the square root of a prime number by our definition or the rule number 1. So you cannot say that one rational is equal to the one irrational number. Hence our assumption that we took in step 1 was wrong. So this cannot exist. Hence we say that 3 minus 2 times square root of 7 is an irrational number. So objective in this part of the tutorial was to make you aware about these three principles, that how do you operate on rationals and irrationals and what will be the result of that operation. Will that result into an irrational number or will that result into a rational number? So with that, we take a pause here, and this concludes our discussion on the concept of real numbers.